We are now done introducing the experiment object and the experiment framework into our code. The whole point of that really was to set the stage for distributed training. And this is the first time that we'll be making use of the Cloud ML engine. This is a service that is offered as a part of the Google Cloud platform. This is a distributed training service, and it's important for us to understand why distributed training services like this one are becoming more and more important in real world machine learning applications these days. So let's very quickly cycle through some of those reasons. Some of them are more obvious than the others. The first, and perhaps the most important and the most obvious, is simply to deal with larger and larger training datasets. We've already seen how carrying out training with a small training dataset leads to disappointing results. This did not change even when we increase the model's complexity by moving from a linear regressor to a DNN regressor. Clearly, our best bet, given that we have a data set of a billion rows, is to increase the size of the training data. And indeed, we shall see that by doing so, we can substantially reduce the RMSE. That's the first reason why distributed training on the cloud is becoming so important. Some of the other reasons are a little more subtle. The second has to do with the need for parameter servers. If you think back to the gradient descent optimization process, you might recall that that process is not all that easy to parallelize. For instance, if we want to have parallelization of different batches within the same epoch, well, then we need some shared memory for all of the model parameters at the start of that batch to be stored and shared. This requires the use of parameter servers, and this is a service which Google's Cloud ML engine helps us accomplish. A third reason for the rise of services like Cloud ML Engine is the increasing importance of hyperparameter tuning. This process was always important in refining a model and finalizing the form to actually deploy to production. But as model topologies and neural network architectures become more and more complex, hyperparameter tuning is becoming both more important and more difficult. Doing so in a non distributed fashion, for instance, on a single local machine, is almost impossible. Another problem, and this is quite a subtle one, has to do with something called training serving skew. To make this real, assume for a second that during training, you calculate some kind of exponentially weighted moving average. So, this is a fairly complex average, a complex formula that you calculate during training. Let's say now that during actual prediction, you no longer have the time or the real time streaming input code to calculate the same complex formula for the prediction. Very likely you would fall back on some kind of approximation like a simple average. The result of this would be that your prediction code or your serving code would now be a lot simpler, a lot less robust than your training code. Training serving skew is a common reason for the disappointing performance of machine learning models in production as compared to during training or validation. Services like the machine learning engine from GCP help us have the same code in training as well as in production, and they help to reduce, possibly even eliminate, the training serving skew. This point about training serving skew also leads us to the fact that decoupling a model from its clients is more and more important these days. We cannot rely on all of the clients of our TensorFlow model also being written in Python. It is entirely possible that we might have web apps which are going to make calls to our prediction model. It should be possible for these web apps to do so using a simple, ubiquitous mechanism such as maybe a RESTful API call. This decoupling of a model from its clients is achieved very easily using ML Engine. And by the same token, just as we can auto scale the amount of compute capacity that we use while training the model, we can also auto scale the amount of capacity that we have for prediction. So, for instance, if we expect our model to receive millions of queries per second, that is also possible to support given a high enough budget. All of these facilities come to us with something like the Cloud ML engine on GCP or its competing services on Microsoft's Azure platform or AWS's SageMaker. Like those other cloud based services, Google's Cloud ML engine offers two services: a distributed training service to scale train models on the cloud, and a distributed prediction service to host those trained models. We are going to make use of both of these in this upcoming demo. Before that, let's very quickly outline some of the ways of interacting with Cloud MLE. Like other cloud services, we can access Cloud MLE using a RESTful API call, using Google Cloud Client libraries, the command line, that's gcloud, or the GCP Web Console. And we can also interact with Cloud MLE using Data Lab. That is going to be our preferred option, which we are going to go with in this course. Let's quickly understand some of the mechanics associated with carrying out distributed training. First, we need to modify our TensorFlow program. We need to create a Python trainer package which has within it a task.py and a model.py. Next, we need to get the training as well as the validation data onto the cloud, onto some cloud storage bucket where it can be accessed by the distributed training service. When we actually submit our model for training on the Cloud ML engine, a trainer package, that's the trainer Python package, is going to be picked up by the Cloud ML engine service and copied onto different nodes, that is VM instances that are called replicas. One of those replicas is going to be called the master, and it's going to take charge of orchestrating the distributed training process. Notice that the training service will not interact with your job or with your TensorFlow code at all. All that it does is allocate resources to the replicas and to wait until the master, which is managing the process, either completes or crashes. And at that point, the training service will go ahead and free up the allocated resources. Let's very quickly understand what happens during that training process. The packages can write to cloud storage, and typically at the end of the successful training process, the trainer package is going to export a trained model. This is accomplished exactly by that experiment framework which we already discussed, and this is why the experiment framework works so nicely with ML Engine. As we shall see, the other cool bit that happens during the training process is that log entries are written to stack driver logging, so we can quickly and easily examine those log entries from the web console. And one last little bit for us to keep in mind is that dependencies must also be handled in a standard manner. This is because our Python package needs to be able to execute on the cloud. Standard dependencies can be installed with just one pip install call, and these can just be included as imports in a setup.py which is contained within our package. On the other hand, custom or non-standard dependencies must also be placed in cloud storage. That is, the Python packages need to be placed in cloud storage. We will then specify the paths to those packages in the job config and go ahead and install them using pip.